Please label these notes integrals 8 notes, variable bounds, and write today's date. By the end of this lesson, you should be able to take definite integrals when you have variables as well as when you have numbers for the upper and lower bounds. So one thing to be aware of is that the bounds of integration, those little numbers on the integral sign, can be variables as well as numbers. Typically, we use a different variable than the one in the function to avoid confusion. So it's entirely okay for us to have problems like this. Find the integral from pi over 4 to x of secant squared t dt. So what we're going to do is we're just going to do the same thing we were doing before. So the antiderivative of secant squared is tangent, and our variable this time is t. That's pretty typical when we have these problems, that this will be t and this will be x. And then our bounds are from pi over 4 to x. So what we do is the same thing we've done in the past. We just substitute the upper bound, so tangent of x minus the tangent of pi over 4. Find those numbers. Well, I guess just the one number. Pi over 4 is 1 root 2. Tangent is opposite over adjacent, so the tangent of pi over 4 is 1 over 1, or 1. And there's our answer. We'll have the x at the end. That's entirely okay. We can also see problems that ask us to have a little more creativity, such as find all values of k for which the integral from 1 to k of 2x dx equals 0. And as soon as we look at this, if we're looking for when this equals 0, for sure, when k equals 1, we're going to have the integral from 1 to 1. Doesn't matter what this is. This could be anything. The integral from a number to the same number is automatically going to be 0. So we know one of our answers is certainly k equals 1, but let's see if there are any others. So when we're doing this, the integral from 1 to k of 2x dx, we take the antiderivative, so that's x squared divided by 2 from 1 to k. So that's k squared minus 1 squared. And we're told that the integral from 1 to k of this function is 0, so we can say that 0 equals all of this. If we add 1 to both sides, k squared equals 1. And if we take the square root of 1 is plus or minus 1. So that means the integral from 1 to k of 2x dx equals 0 when k equals 1 or k equals negative 1. We can also do problems where we're doing both the derivative and the integral. So let's say that capital F of x equals the integral from 3 to x of 4 cubed dt. What we're going to do is we're going to find the derivative with respect to x of this capital F of x. So the first thing we can do is just our normal f of x. The antiderivative of 4t cubed is 4t to the fourth divided by 4. And our bounds are x to 3. So we've got x to the fourth minus 3 to the fourth, or f of x equals x to the fourth minus 3 times 3 is 9, 9 times 9 is 81. Now, when we go and take the derivative again, when we take the derivative here, we're going to bring down that 4, subtract 1 from the exponent, and then the derivative of a number is just 0. So we just end up right there. Notice something really interesting. This right here is the same thing that we started out with, except that this t has been replaced by an x. And that makes a lot of sense because when we put in this number for the bound, we're going to get out just a plain old number. And when we take the derivative, that part goes away again because the derivative of any number, regardless of what it is going to be 0. And here, when we're doing the integral, the first thing we do is take the antiderivative. And when we take the derivative of that, we end up back where we started, right here. So this is actually something that can be generalized to create what's called the second fundamental theorem of calculus. The derivative of the integral from a to x, where a is any constant number, f of t dt equals f of x. So this just says when we take the integral with variable bounds, should say a variable for a bound, and then take the derivative, the result is the original function with the variable replaced. Notice this is only true if this is a variable. If these are both numbers, then we've seen before what we come up with at the end when we take the integral, so we come up with a number. When we take the derivative of any number, it's 0. So if we have the derivative of integral where these are not variables, the derivative is always going to be 0. This only is true when we have a variable for one of our bounds. So this makes for a very, very nice shortcut for problems like this. Find the derivative of g of x if g of x equals the integral from negative 100 to x of the following: root 3t minus 7 over the cosecant of t minus 1 with respect to t. Now, one thing we could do is we could do our usual how to take the integral and try to figure out the antiderivative of this and plug in x and plug in negative 100 and subtract them and all that kind of thing. The problem is this is going to be a huge pain in the neck because we actually don't have a formula for the antiderivative of the cosecant of t, and this is just a huge monster. But what we can use is we can see that we're going to take the integral and then we're going to take the derivative again to get g prime. So when we do that, when we take the integral and then take the derivative again, we just end up with the original function, but this variable has been replaced by this variable. So we can just look here and say g of x is going to be this original thing, but we replace the t with an x. Done. Way faster than anything else we could do. We can also use that property if we are finding the derivative at a particular value of x. This is our final problem. Find f of 1, actually f prime of 1, if f of x equals the integral from 7 to x of 3t squared over 7t minus 8. Looks like it might be doable to find the antiderivative of that, but we don't have to because we're taking the integral and then we're taking the derivative again. So we can just say that f of x equals 3x squared over 7x minus 8, or I should say that's f prime. So f prime of 1 just means we put 1 in for the x, and there we go. Sometimes the bound is a function rather than a single variable. Like x. This is very similar to what we just did, namely substitute in the variable bound, but because we have more than x, we need to use a variation of the chain rule. Just like if we were taking the derivative of a composed function with a normal derivative. So that means in general, the derivative of a function from a to f of x, g of t dt, equals g of f of x, so that's the substitution right there, times the derivative of f of x. Let's look at an example of this. Let's say we're taking the derivative of the integral from -1 to x squared cosine t dt. Just applying this rule, we can see that we're going to substitute the variable bound in like we were doing earlier. Then we're going to multiply that whole thing times the derivative of x squared. Giving us cosine of x squared times 2x. Let's show why that's the case over here. Let's do it all out by hand. The antiderivative, or excuse me, the integral from -1 to x squared cosine t dt. The antiderivative is sine t from -1 to x squared. That's the sine of x squared minus the sine of -1. This is just a number. So when we go to take the derivative, We're going to take these two separately, but the sign of -1 is just a number, so that's going to become 0. So we're really just doing the derivative of sine x squared. So that's a box function, so we are going to take the derivative of the outside times the derivative of the inside. Voila! Matches just what we had there. One thing to note with all this is that the chain rule piece is going to be multiplied by everything. So for example, the derivative of the integral from 0 to sine of x of t squared minus 3t plus 1 dt, that's going to equal, replace it, sine of x squared minus 3 sine of x plus 1, and then this whole thing is going to be multiplied by the derivative of the sine of x. And that's because when we do the antiderivative, even if we have just a plain old number here, it's going to acquire a variable when we take the antiderivative. And so this sine of x is going to get substituted into it, and we take the derivative, we're going to have that piece for that chain rule. So let's do our final step. Derivative of sine x is cosine x, and make sure not to forget these parentheses. That's how we know that this cosine of x is multiplied times everything. Let's give you a check for understanding problem, and then we'll be all done. Find the derivative with respect to x from -1 to 3x squared of the square root of 2t cubed plus t with respect to t. In this case, actually, we can't even take the antiderivative by hand, because when we try to do our u substitution with this, there's nothing for the t cubed derivative, so 3t squared, to cancel out without here. But fortunately, we don't need to, because we know this second fundamental rule. So we're just going to start off by substituting. Actually, this is a check for understanding problem, so you should go ahead and try that on your own, and pause the video now. Okay, so the way that we do this is to substitute our bound in, so that's 2. Substitute the 3x squared into both of the t's, and then multiply the whole thing. We put parentheses there for added clarity, but in fact, because this is all under the square root, it's all in invisible parentheses already, times the derivative of 3x squared. So this is 2, 3 cubed is 27, x squared cubed, multiply the exponents, that's x to the 6th. Derivative of 3x squared is 3 times 2, that's 6x. 2 times 27 is 54, x to the 6th, plus 3x squared. And voila, there's our answer. This concludes these notes.